Good morning again. Sorry for having my system muted. And what I mentioned early on, I said that we need to look at tutorial number 1 and tutorial number 2, where Mahmoud has provided quite a bit of details on how to utilize the computational environment so that we are able to create either a model based on multi-layer perceptron or any other type of neural network. So my first statement during this lecture was have a quick look at the material on the tutorials, and it showcases you examples on how to run multi-layer perceptron, because we have these particular representation, these particular models required in assignment number 1. You can utilize any type of library, you can utilize any type of software as long as you resolve the problem, but you have some examples because I received some emails from some of the students asking how to run this, how to do this. I know that a number of the students taking this course have never run a machine learning algorithm. So you have the ABCs of how to do that using the tutorial number 1 and tutorial number 2 that were recorded by Mahmoud. So spend time on those ones, understand them, and you should be able to utilize that material quite easily. So I said that I went last time, so let me go back here and I don't know here. So we spoke about this last time, and we said that when we speak a particular model or a complexity of a model is dictated by mostly the number of nodes within the neural network structure, or also it is dictated by the polynomial order in the case where we are using regression. We don't use a neural network since we are utilizing here artificial neural network systems. So we mean the more we have a number of nodes or a number of hidden layers, the more we speak about the complexity of the model and the high order of the model of the neural network system. So we speak. So this is an interesting slide. I would like you to understand it well. So that's why I came back to it. So we pick a particular type of model. We run the training and validation at the same time. So we run the training model, the training parameters, which provide us with a trained model, which would provide us with the model, and then we check on that particular model on the validation. So we have 3 items here. So we have the number of nodes that we suggest within a particular neural network, and then we run the training data to extract the hyperparameters of that particular neural network with that particular number of nodes. We call them hyperparameters of the neural network. And then we check whether the validation, which are the testing type of data within the set of the training data, because remember we said that we have, last time we spoke about testing data, training. We spoke about validation type of data, and we spoke about testing data, which are the data that we utilize them at the end once we have created the most optimal type of model for the system. So we check on the validation of the model, and then at a certain point, the validation set is not improving in terms of low error performance, while training error keeps decreasing. So at this particular stage, we stop the training and pick the model that led to the lowest validation error. So if we go back 1 slide, this is that particular area. So as soon as the validation error starts increasing, we stop and we take the value where the system, has had its model just before the validation started to increase. So we keep track of the models that have been trained, and then we calculate the validation every time that we have a particular model we created with the training data. And once the validation started increasing, we say that we should go back to the earlier, just the model that we just trained earlier, just at this particular stage, and we consider it as our best possible type of model. So that's what we mean by early stopping. So we spoke about this last time, and I'm repeating it here. And then we repeated with different type of models. What we mean by different type of models, it is with different type of nodes, because we would like to check what is the best possible number of nodes that has led to the best possible error. So for one particular training model here, we have the best possible error between training and validation. But we go further, we test several other type of models, and then the overall system that provide us with a particular number of nodes and the lowest number the lowest value for the training and the validation error is the model that we have to select. So that's what we meant by early stopping in the earlier lecture. So now I go to the cross validation, and as I mentioned to you, the cross validation is a system that is composed of a number of portions. So we divide them into k-fold elements for the type of training. And when we speak of k-fold cross-validation, it simply means that we divide the overall training data, which includes the validation, and then we took one portion of that k values, so we use it for validation, and the remainder k minus 1 are utilized for the training model. So this is k minus 1. And this is going to find it in problem number 3. So the number 3 tackles the 10-fold cross-validation. So that's what we meant by cross-validation. And this is what we meant here, because this training data here that we took, remember that the testing data is something that we have already hidden here. So in assignment, I told you to consider this as 20% of the total number of all the type of data that we have in the system. This is 80%, and within this 80%, we divided it into 10 portion. So each portion is considered as validation data, and that portion could be at the start, it could be in the second place, or it could be at the last place. So for each one of these k-fold validation, you try to find the model 1 here. So we call it model 1. Here we call it model 10. Okay. So you run each one of them, you compute the error for training and the error for validation. It's a little bit difficult to write on, with the mouse, but this is basically for each one of them. And then what you do, you take the average for all these type of model. Okay, so the average, that's the average error for all these type of model. Remember, this k-fold cross-validation, we do it for each model for which we are changing the number of nodes. So for assignment, for instance, we start with number of 10 nodes, 20 nodes, I think, and then 70 or 40 nodes, and then 100 nodes, okay? So each one of these is what we call it a model with a certain complexity. So this is the simplest model, this is more complex model, this is more complex, and this is the highest complexity model. So for each one of them, we run the k-fold cross-validation. So that's in assignment number 3, what I meant by the number of nodes and by the number also of the training data for each one of them. So we utilize the cross-validation for that particular element. And when we say that the training, or we stop the training and we create our model, is when we have the training and then the validation at this particular stage. So this is what we call the early stopping, okay? So for the early stopping, that's where we stop and we say that we have a particular model with the minimum error for training and minimum error for validation. So I would like you to remember this slide, and that's what we mean by k-fold cross-validation. This is what a lot of people are utilizing nowadays in the field of machine learning and in the field of data training to avoid overfitting and to make sure that the model that has provided you with the best average error is going to be the best model for the system. That's the model that you have to select. So let me, yeah, so this is what I just mentioned here. So for each k-fold cross-validation, you create a model, then you create the evaluation, you create a model, and then you create the evaluation in terms of the error, then you create a model, and then the evaluation, and then you take the average of all the models. That's what I just explained in the earlier slide. Okay, so this is how this is now it summarizes what I just mentioned. So to build an adequate model while making use of the k-fold validation, proceed as follows. So this is the systematic way. Choose the type of model M you want to test. So it's either linear regression, polynomials, A and N with different hidden nodes. So here in the particular case of this course, we choose an artificial neural network with a particular number of nodes. So we start with the smallest number of nodes, okay, of nodes. So we start with model 1. So let's suppose that we start with this model 1. For each model M, so this is model M1, let's say, we run the k-fold validation and average out the validation error among all k-folds. This is what I mentioned in the earlier slides. Run this operation several times. So why we do it several times? Basically to reshuffle the data in between the k-fold validation, cross-validation. So what we mean? I mean, the first place become, I mean, so we, at first we choose a data, so let me explain here. So at first we choose a certain type of data, and then we reshuffle this data so that we don't have the same location of this type of data for the second running of the k-cross validation. So cross validation for a certain set of data, we run it 5-10 times. So you can merge, you can reshuffle it every time that you are doing cross validation. Okay. So this is what we do for each model, run k-fold, and we run this operation several times to ensure that the data is well mixed, because having a data that is well structured and ordered is not good. So we have to have them in a random type of behavior. And then and there is no memorization, because we don't want to memorize when we do a k-fold cross validation. So we don't want the system to remember the order by which we have chosen the validation. And then what we do, we change the model by changing the number of nodes. So if we start with 10 nodes, now we go to 20 nodes, and we do exactly the same thing with the k-cross validation, and we check again the average of the error for each one of the models. Okay, the model with the smallest validation error among all the models with a different type of nodes is the model that we are going to select ultimately. Okay, so now what we do, once we have that particular model, so let's say it's the model number 4, which has possibly 40 hidden nodes. So model number 4, now we take the training data, which includes the validation and the training. We create the full, I mean, we utilize the full range of the data, train it again with that particular set, and then we do the testing. So we utilize then the testing which the system has never seen before. So this is the testing set of the data. Okay, so after we have gone through all the k-cross validation, then we do the testing for that particular type of model that we have created. So that's how we do the selection for the k-fold validation. And if you follow the step-by-step in assignment number 1, problem number 3, this is exactly what we mean by that. So in summary for this particular version of the, for this set of slides. So when we are dealing with underfitting, where we have high bias and the model is simple, occurs when the training data is not enough, or when the model is too simple, when we have possibly 1 or 2 nodes within a neural network and the function is highly nonlinear. Hence, what we do, we try to increase the training data, but sometimes we don't have the ability of doing that. So what we try to do, if the data is, I mean, we are not able to do that, we try to increase the complexity of the model until good testing results are provided, which means we do stop the training once we have an excellent training error and an excellent validation error. Overfitting, on the other hand, happen when we have high variance. Why we say it's high variance? It means that the system that has been built using a particular set of training data is not valid for a set of testing data, which means that we have variety of models. So the model that we have built for training is not valid for testing, and this is not good for generalization. So this happens when the model selected is too complex, when we have very high number of nodes for that particular type of models, or we have high degree polynomials in case we are utilizing a regressor based on polynomials. And also the training data is not enough to describe the entire population. So the worst combination is when the model is very complex and the amount of data is very low. Then for sure you are going to have overfitting. So what we do there, we try either to increase the amount of data and lower the complexity of the model, or keep the model as complex and try with larger number of training data. If the training data is not possible to increase it, then try to reduce at least the complexity of the system, and also try to stop when the validation and the training process have reached the lowest value of the error. So overfitting and overtraining, sometimes we call it overtraining, when we keep training the system until the validation error becomes very high, are two equivalent concepts for this particular behavior here, for complex model and for high number of epochs for the training of the system. So in order to avoid the high variance of the system, so we create a model that is less complex, and a model for which the error stops, for which the training stops when the training and the validation have very low values of the error. So that's the major observation that I wanted to mention here at the end of this set of slides. And you are going to infer this particular conclusion when you are going to look at it in assignment number 2. So this is what I wanted to share with you in this set. So let me go here and summarize what I mentioned during this, this set of slides. So we have the initial data set of the system. So this, I took it from Shanine, who has a website. And I like this figure because it provides you with an excellent way for understanding what we mean by this. So the initial data set, so related to what we are doing here. So let's suppose that the data is clean, is created, and we remove redundant features. We will speak about this in the future. So this is the input variable. This is the output variable for a given system. And this is the data splitting. I would like you to look at it here. So this data here is divided into 80% and 20%. So you see the green here and you see the blue. So here, for this 80%, we are going to utilize it for a component for it is if we are using the k-fold cross-validation. So 90% will be used for training and 10% will be used for validation. And when we do the k-cross validation, so we reshuffle the value, the location, the part of the validation, so that we have several types of models that are trained using the trained model and the cross validation. So this is what I just have been speaking a few moments ago. So you have the training set, you have the test set. Once we are happy with this particular type of model, then we are going to utilize now the 20% for which the system has never seen for the training model, and we use it for this particular purpose to say that now, look at the blue here, we have the best possible model, and this best possible model is going to provide us with the predicted type of values, okay? And then we are going to evaluate this model performance using some of the tools that we are going to speak about today, and we are not going to talk about them. I mean, in the homework. So in the assignments, I did not specifically ask you to work on these particular components in a qualitative type of way, the main thing is to have the best possible error for the training and the cross validation. So this is an excellent diagram. I like this type of diagram which summarizes what we have been doing so far in terms of training, validation, and testing, and then what we are going to see today in the form of evaluating the model performance. So now let me take a few questions before I go to the next set of slides. So I will be happy to hear some of your questions or to see some of your comments on this one. So if he manually dismisses them because I got dismissed. So, oh yeah, so yeah, sorry for that. Okay, Professor, can't hear you. Okay. Sorry, I did not see these messages because I was focused on my slides. So yeah, I will make sure to look at your messages in the future. Okay, I can't. Okay, so I am not seeing any questions here. So okay, so there is one question here. So cross-validation is for getting a better characterization of the performance of the model, right? Yeah. So cross-validation again is a way for assessing the model by not using all the training and the testing data. So what we mean by that? So so instead of testing the system with 80%, building a model with 80% and testing it with 20%, okay? So we are using the cross-validation. So we divide this 80% into K cross-validation. So we create a portion of it, which we utilize it for training of the system, and then we test it here, okay? So this is what we call it validation. So before we attack or we utilize the 20% of testing, we try to create the best possible model based on the K-cross validation. So this, when it is used, when the number of data is not very high, because as you saw earlier, when the number of data is not very high, whether it's for high bias or for high variance, the system is not able to provide you the best possible feature. So what we do, we try to increase that number by making usefulness of all the data in the training set. So we don't touch the testing set at first, okay? And we create the best possible model with this model for which it has training and it has validation. Once we extract the best possible model from all these type of sets, then we utilize it for testing our particular model, where we have utilized now not only the 90% of the training, but we utilize the 100% of the training data once the average of the K-cross validation is the smallest. Okay, so the other question, we take the average accuracy and say that the model that we got from one of the K-fold variation has accuracy A, which is actually the average of all the accuracies from all the K-folds. So again, yeah, that's basically what we do. So first we take a model M. Again, model M is characterized by number of nodes. Okay, that's model N. For this particular model M, we create K-fold cross-validation. So basically, in our case, we create 10-fold cross-validation. So we create 10 little models. Remember, we're still in this model M here. We create 10 little models for this one. And then we check on the average error divided by 10. Okay, so we record this average error. So let's suppose that it's error 1 for this model 1. Okay, and then we continue for model M. Model N has particular number of nodes subscript N, which is more complex possibly. Okay, and then we do the cross validation, k-fold validation for this particular model. And then we create the average error. So we have the average error, which we call it En. And then what we do, we go to each one of these average error and we select the smallest. Okay, so the smallest among all of the error is going to give me the M of whatever we call it K. Not K, let's call it MZ. MZ is a model which is residing between model M and model N, okay? And that model is the one with the smallest error. So this is how we create the average accuracy for each one of the models, okay? So we select a particular model, we create the k-cross validation, we create the average error for each one of them, and then among all the models we have selected, we look at the model that provided me with the lowest average error, okay? We say that the model that has provided me with this model. So once we have this one model, so then we are going to train it now with all the training data, because we are secure about this model that is going to provide me with the best possible type of model. And from there, we test it with testing data to make sure that the error is, very, very minimal and within these ranges of the lowest value of the small error. This is the model that is going to be utilized later on, either for, outside use or for future prediction. That's the model here. This is the model that I told you, which is the predicted type of values model. Okay, is this understood? Okay. So the full 80% and no validation data, we still leave the 20% remain. Yes, correct. So again, this 80% contains the training of the data and the validation. This is going to provide us with those average error. Okay, so these 20% are going to be utilized only later on after the system has finished with all the average error. And that's the testing data that the system, that's where we say that this is the predicted model, the testing error is this, the training error is this, and we are sure that this is the best model that is being trained and that we are going to utilize for prediction and for commercialization if you would like. Okay, so again, after we do the average, we create the training model with the whole 80%. And then that particular model for which the average error was the minimal is going to be utilized for testing. Okay? Okay, thank you very much. If you don't have any other questions, let me go now and speak about another major aspect of this course, which is known as performance measures for machine learning models. So far, we have discussed this aspect of the system for which we have to balance it out between overtraining and undertraining, or overfitting and underfitting. And problem 3, when you are going to tackle it, you are going to see that you are going to understand all this type of concept and you are going to infer all the conclusion we have studied in this set of lectures. Okay, so feel free to let me know, so you can write your messages and then I will respond to them in the next 10 or 15 minutes as we progress with the lecture. So let's talk about performance measure for machine learning. So what we spoke about now is the philosophy of building a good model. But in order for us to speak qualitatively about this particular type of model that we select, you cannot tell me, oh, this is the best model because we have obtained the lowest average error, or we have run the k-cross validation. I need more from you. I would like you to get some qualitative type of information, and this is what is known as performance measure. This applies for classification and also it applies for regression. Okay, so we are going to see these particular aspects in this set of slides. Okay, so let me mention here. Page display, single page. Okay, so after creating machine learning models, performance measures are needed to compare performance for different models, parameters or approaches. So this is the qualitative aspect that we do in various type of representation here. Okay, performance measure for classification, we are going to see both for classification and for regression. Let's look for classification. I'm sure that some of you have heard about some of what we are going to discuss next. So when we are doing a certain type of classification, we are sometimes going to classify something correctly. Sometimes we classify something wrongly, something that needs to be correct, but it was classified wrongly. And sometimes we need to classify something that doesn't belong to that particular class. That's something that is what we call true negative. So true positive, we define it as what the system is expecting when we define something as positive or what we are desiring. A true negative is what we call that the system is not, what the system is not classifying as positive, something that we don't want it to be classified for our system. We would like to reject it, for instance, and it is what we call the actual negative, the true negative. But sometimes we have some items that are estimated as negative, but they are actually positive. So let's look at them here. So this set, so let's define it, this set. So let me go here, utilize this pen here, okay? So these particular values here, this is what the system is estimating as positive, and the system provided them to us as positive. These has been estimated as negative, but actually they are actual. So they were estimated as negative, but they were actually actual positive. Okay, so this what we call them false negative. Okay, so these true positive, and here we call them false negative. Okay, the same thing here, estimated as negative. So these are the actual negative. Okay, so this is a class. So let's suppose that we have two classes. We have the class of a dog and the class of a cat. Okay, so our system is going to look at a dog and it says, oh, this is a dog. Okay, and then it's going to look at the dog and it says that, oh, this is a cat. Okay, so that cat, it's not a cat actually, it is a dog. So we call it, it's a false negative. So we have estimated it as belonging to this particular type of class. Okay, so this is the false negative and this is the true positive. So here we have the true negative, and these ones, they were estimated as positive. So we call them false positive. They were estimated as positive, but actually they are negative. These ones, they should be cats, but we suggested them as dogs. So dogs here as positive. So we claim the dogs as positive and the cat as negative. So the system has to provide us with positive and negative. So the dog is supposedly the true positive. So some cats are going to be, some dogs are going to be classified as dogs. We call them false negative. So this is the light red here. And some cats are going to be estimated as dogs, and we call them false positive, and this is true negative. So true negative is the cat, true positive is the dog. So this is what I would like you to understand at the start when we are going to define these elements for classification. So in a binary classification, so this is the definition, the formal definition. So true positive is predicted as positive, and the estimation, this is the system that we built to predict, the estimation is correct. So this is actually in a positive class. True negative is the other side. So this is the cats. The system predict them as negative, predict them as cats, and they are actually cats. Okay. So now let's look at the false positive. It is predicted as positive, but the estimation is wrong. Okay, so it is predicted as positive, but it should not be predicted as positive because it's a cat. So this is a false positive. We call it false cat. So it's false dog because it's cat. And the false negative, this is the false cat. False cat. False cat. So predicted as negative, so it's predicted as cat, but in reality is a dog. So that's false negative. So in order for you to remember these things well, true positive and false negative, how they are related to each other. So true positive, so this is a sign of plus. So true positive, true plus. And here is false negative. So it's minus times minus. And this is a plus. So for you, a false negative is actually something that has to be predicted as positive. Okay, so I would like you to relate these false negative with the true positive, and the same thing true negative here, which is not a minus, which is the cat, and then it's false positive, so it's minus plus. So it has predicted, I mean, the wrong. So this, it's a cat, but you have predicted it as a dog. Okay, so this provides us with a negative. So true negative and false positive belongs to the same. So this is exactly what we mean. So this is plus here, and this is minus minus. This is minus, and this is plus times minus, which gives you minus. This is product. This is product of minus and minus. Okay, so that's one way of doing it. So let's look at these particular, what we call the confusion matrix. Confusion matrix is an important concept in the area of performance, and I would like you to understand it well here. Okay, so we have the actual label. So the actual label, it means the reality. Okay, so this is reality. This is what these systems are. Okay, so I apologize again about the writing here and about the early muting. I mean, it's a little bit difficult to teach these online lectures, and thanks for letting me know about this. Okay, so this is the actual label, positive, negative. So this is, if you would like to remember it, dog and cat. Okay, and these are the predicted level. This is what the machine, the artificial neural network, is providing us. Okay, so if you are predicting something that is correct, positive, positive, so we call it true positive. If you are predicting something positive, but it is actually negative, it's called false positive. So you predicted it as positive. So it is actually a cat, but you predicted it as a dog, because the positive here are the dog here, the cat. So you predicted a cat here, which is supposed to be a cat, as a dog. Okay, so this we call it false positive. The same thing here, true negative, these are perfectly cats, and they are predicted as cats. So you can see that their label is cat, and they are predicted as cat. So this is the true negative. Finally, the false negative here. So this you predicted it as a cat, because that's the negative cat, but in reality it is a dog. Okay, so this is false positive, false negative. So here the sign, if you would like to remember the sign here, and this is the sign here, and the sign minus here. Okay, so I would like you to remember this representation of the confusion matrix. So now let's, after we created this confusion matrix, then we are going to start making some definition. So the first definition that we call, so this is an accuracy. So you are going to hear lots about an accuracy of a classifier, including in the assignment. So you can tackle problem number 4 with accuracy, with the F measure, and with all type of measures that we are going to talk about that. So the accuracy is the set of correct prediction, true positive plus true negative. So this is true, this is true. So this is the correct prediction, and divided by all the classes. So true positive, true negative, false positive, false negative. So this is again what it is. So the accuracy, it's computing true positive plus true negative divided by all the classes included here. Okay, I will give you some example shortly. Then we define other type of measures. We define the measure of precision, and we define the measure of recall, and that will give you the difference between both. So the precision is simply the true positives, TP, divided by TP plus FP. The recall is a measure that ratio of estimation as a class are correct among all points that actually belong to that class. So here all actual positive classes. So positive classes are true positive and false negative. So the recall pertain to the true positive, how many you have estimated correctly, but also divided by what we have as positive classes. So either the true positive or the false negative that is supposed to be a true positive, but you did not classify it as such. So this gives us the recall measure, and this gives us the precision measure. What is the difference between both of them? There are a number of differences here. Let me continue with the F beta score. The F beta score, before I give you more about these ones, and I'll give you some examples when to use the precision, when to use the accuracy, and when to use the recall. So the F beta score is simply a combination of precision and recall. Okay, we call them, it's F beta. Usually we utilize the F1 measure. The F1 measure is the most used in the literature. Okay, so we utilize the F1 measure. So this is the general one, okay, but this is the most used in the literature. So when you speak about an F1 measure, it pertains to the precision and the recall. So it is a combination of the precision and the recall together, because we are going to see that precision sometimes is important in certain application, and recall is also important in certain type of application. And if we would like to combine both of them, it gives you a certain way to showcase you how the precision and recall are pertaining to each other. What is the importance of which element? Is it the precision is more predominant, or the recall is more predominant? And usually, all the time, the F1 is located within the values of the precision and the recall, whether the recall is the smaller one or whether the precision is the smaller value among both of them. And I will show you also an example in a few short moments. True positive rates and false positive rate also have been utilized in the literature. I'm not going to emphasize a lot on them, but I would like you to remember their definition. The true positive rate is actually the true positive here divided by all actually positive points, I mean, which is the true point plus the F false negative, which is no other than the recall. Okay, so the true positive divided by TP plus Fn. So this is the recall measure. So we call them also in this way. The FPR, the false positive rates, provide us with the number of false positive divided by the false positive plus the Tn. So here we are tackling how many false positive have been registered when the system is within the range of the true negative, and when the system has expected something that is negative but it estimated it as positive. We call it false positive rate. Okay, error rate here is given by ratio of incorrect prediction to total number of samples. So the system here is providing us with how many you have found false negative and how many we found false positive with respect to all the classification values. Okay, so we call it the error rate. It's also utilized from time to time in parameterization of the error performance. Specificity also, it is sometimes utilized, and it's the proportion of the negative data points that are correctly classified as negative. So this is the true negative divided by the true negative plus the false positive, which are in the same range. So true negative and something that is falsely predicted as positive. So it is, so here as you can see, this is negative and this is negative and this is negative. Okay, so this is what we call specificity for these systems. Okay, so I'm not going to talk about the the receiver operating characteristics curve, so we are not going to tackle it, but also sometimes when you see it, it is a characteristics that is related to to showcase you the behavior of a classifier with a true positive rate and false positive rate. So these, I mean, when we are trying to draw this particular picture of the classifier between these particular values and the particular values, so the more the system goes to the false positive rate, the worse for that particular classifier. The more you go to the true positive rate, the better is for your system. So this is a figure that is known as the receiver operating characteristics for the system, and sometimes we find it in certain type of performance measure for machine learning system. Let's look now at a multi-class confusion matrix before we go to some examples. Okay, so multi-class confusion matrix is when we have more than two classes. So for the examples number 4 in the assignments, we have 3 classes. So we speak there of multi-class confusion matrix. So the multi-class confusion matrix, so you have class 1 here, so class 2, these are the real class 3, and class 4. And here is the predicted classes, predicted class 1, and this is predicted class 4. Okay, as you can see here, these are what we call the true positive, because the class 2 and the predicted class 2 are the same. Okay. Okay, every part that is not part of this one, so here is going to be the false positive, the false positive for each one of these particular values. So here we have the false positive for this class here. So this is predicted class 2. Okay, these are the false positive for that class 2, false positive for that particular class. Okay, so this is what we define here for that particular class. So sometimes we take a particular class and then we say that for that particular class, all the ones here from this particular level here are false positive for that particular class, false positive here, false positive here, and then false negative with respect to this particular type of class. So here is false negative with respect to this class, false negative with respect to this class, false negative with respect to this class, because we have, I mean, this class, and we have all the pertinent for the other one that are not related to that particular class. And then if we would like to estimate for this particular class, so this is false positive here, this is false positive here, false positive here, and for the other ones is going to be false negative. So false negative for class 2. Okay, false negative for class 2. Okay, so you take for each one of them and you create the false negative for class 2. Okay, usually that's what we do. We take one particular class and then we compute the other ones as the other class. So this is one class, and all the 3 other classes are going to be the non-class of that particular class. So that's basically what we mean by multi-class confusion matrix. Okay, so let's look at some examples here to illustrate what we mean by all these particular elements. So we assume here that a model that classifies emails to be either spam, class 1, or non-spam. So the positive here is C1. So the spam is C1. So we would like to take all, we wish to have all spam emails to be discarded from us. But also we would like to make sure that real ones that are negative should not be discarded. So a good email should come to me. Okay, a good email should come to me, and it should not be considered as a spam. So we don't want to have a false positive. So for this particular example, we don't want to have a false positive for the system. So let's look at this particular system. So the system was able to classify spam as 80% true positive, and then it classified a spam as a non-spam. So this is spam, but it is actually non-spam. So this is bad behavior. We don't want it. So we would like to minimize. This should be minimized. Okay, so in other case, so what is the thing that is going to be minimized here? So we speak about the precision. We will see the precision for this system. So the precision is pertinent to this particular value. So the precision here is given by TP divided by TP plus FP. Okay, let me go back to precision. So precision is TP divided by TP plus FP. We would like to have the highest level of precision. So we would like to minimize the false positive. Why? Because if an email that is legitimate goes into the spam, that is bad for you. You don't like that. And you are waiting for an important email, and that email goes to spam. You don't want it. So in this particular case, precision is very important. So depending on the problem, you select what type of classification measure for your system. So let's continue with the accuracy. So the accuracy, we find it to be 70%. So this system has estimated a spam that is actually false negative. It was, a spam, but it was not, it is a spam, but the system selected it as non-spam, so it's false negative. And then you have here 130 true negative, which means legitimate emails. So you have 130 legitimate emails, you have 80 spams, but actually you have 80 spams, and also 80 of them should be in this particular location, but unfortunately they are in this location here as false negative. So the accuracy here doesn't tell us much, but the most important component is the accuracy for this particular system. Okay. So let's look at this particular model here. So let me see here. Okay, so let's look at the value for the precision here for the system. So the precision is going to be 80 divided by precision 80 plus 90 plus 10. So it's equal to almost 89%. Okay, 89% is okay, but when you are dealing with problems, so this is the precision. Okay. So for this particular system, the precision is the most important value, because we would like to have the lowest elements of the false positive. So in this particular case, we don't want to have system that provide us with lowest value of the, we would like the system to provide us. So the lower is this number, the better is your classifier, because then it can go up to 100% in precision. So for this particular problem, where we would like to minimize the false positive behavior of the system, precision is an important component for your system. Okay. Another model was trained and tested on the same data set. Calculate the accuracy and deduce which model is better. So this is another model that has been trained on the same data set. So we found for this model 70%. For this classifier, so two students have provided two type of classifiers. So one student found 150 true positive, 90 true negative, and the accuracy is 80%. So we might say that this system is better, but we don't know. We have to look at the precision because the precision is what matters in this particular case. So let's look at our problem here. So for model A, we found that the system provided us precision of 0.89. The model B, while the accuracy is higher, remember, the accuracy is higher, but the model provided me with 0.75. Which model is better here? For this particular system, model A is better. I don't care about the recall, 0.5 and 0.94. They are good elements, but it doesn't tell me the whole story. For this particular problem, we would like to minimize mails that go into the spam. For this particular reason, the metric of the precision is the most important one. Okay? Remember what we said about the F1 score. F1 score is always between the value of the recall and the value of the precision, and it is oriented toward the lowest value of the recall. So 0.64 is between 0.5 and 0.89, and it is closer to 0.5 than the precision. That's what the F1 score. The same thing here, as you can see, it's between the F1 score is between 0.75 and 0.94, and it is closer to the 0.75 value for this particular system. Okay, so for these metrics, we can make the following conclusion. Precision. Model A is less likely to mark an email as a spam and be wrong, but is more likely to miss a spam email. So what does that mean here? This particular problem here, because of the recall, is small. So what does that mean, recall small? The recall is small. It means that we are most probably to miss a spam. So the spam goes to your mailbox. That's what it means, 0.5 here. So the false negative, which means false negative, which has to be, I mean, it should have been a positive spam, the system has recorded it as 0.5. Okay, so it's low. Here, 0.94. So here, the spam, you are not going to get a lot of spam. But here, this is negative because the system is going to let filter good emails to go into the spam. We don't want that to happen. Okay, so in this particular problem, the recall is less important than the precision. Okay, so I would like you to understand these type of things. And of course, for different classification model, different type of problem, for different type of metric that is utilized. So in this particular problem, precision model A is less likely to mark an email as spam and be wrong, but is more likely to miss a spam email. So if your main goal is to have emails coming to you that are robust, that are real email, and you don't want to miss emails because you don't go to the junk box and look at it, then you choose precision and you say that classifier A is better. Okay, the true negative rate here, model A is better at detecting non-spam email than model B. Okay, now that this can be due simply marking all non-spam bias. Okay, so this basically type of model is good for the true negative rate. We don't want to have good emails going into the spam box. Okay, however, for the recall, model B is better at marking emails that are spam as spam than model A. Recall is good here for model B because it was able to not bring you as many spam emails as you want them to be. So you don't want to have 100 spam in your online box. However, this model is bad. Why? Because this model could take some of your emails and then put them into the spam. Your real emails, you find them into the spam, something that you don't want to like. So in this particular case, precision is more of a better metric for performance than this particular type of model. Okay, so we deduce that the choice of model depends on what kind of performance is favorable to the use case. Okay, so this particular example showcases you how to utilize these particular systems for this particular performance. Okay, so another example here, and okay, and I will stop in a few moments, but I would like to go over this example very quickly. Consider a classification problem for whether a person in a population of 10 people is tested positive or not. Okay, so it's tested as infected. So this is another problem. And we are going to see here that precision is not more important than the recall. So what we would like to do here, we would like to make sure that the false negative, which means that a person who is infected, but the classifier has classified it as non-infected. We don't want that to happen. Because if a person comes to you in a meeting and he says that, oh yeah, I have tested negative for COVID, but that person was not tested, was tested negative, but it was false testing. He has the COVID. We don't want him into that particular room. Okay, so in this particular case, we would like to minimize as much as possible the false negative. So false negative has to go down. We don't want a lot of it. Okay, so let's look for ID person. It was actually infected and the system predicted it infected, so true positive. He was actually infected and the system not infected, and the system said non-infected, true negative, non-infected, non-infected, true negative, and then actually infected and the system predicted infected, true positive, non-infected, true negative, and look here, we start. So he's or her, she is infected. She's not infected, but the system predicted she's infected. That is fine. I can accept that. So a person who felt that he's not, they said, oh, my test came as an infected. We don't want him in the room anywhere. Okay, but it's unfair to him, but for the community is good. But look at the bad case. He's actually or she is actually infected, but the system tells you she is not. This is bad. You don't want that to happen. This person is not actually not infected and the system predicted non-infected. This is actually infected and the system predicted infected. No. So this is also false negative. So these ones are red flag. So we would like to minimize those ones. How to minimize them? With the recall. Recall is becoming important here. Let's look at these values. So in this particular case, we have true positive 2, TNFP equal to 5, false positive 1, and false negative 2. This number should be very small. This number should be 0. We don't want to have people in our room who are infected. Okay, and the system here classified them. The tests of the whatever, COVID or any other type of disease showed that that particular person was not infected, but actually he or she is. So we would like to minimize this number. So you see the classification things, how it works. Sometimes we would like to minimize this number as the spam, and other times this particular system. The same thing as for diagnosis of cancer or anything, we would like to have false negative as minimum as possible. We want it as minimum as possible. So let's look at the system here. So the accuracy is 70%. Precision is 0.67. Recall is high, it's equal to 0.5. And as you can see, the system is tilted toward the recall. So that's the F1 measure more than the precision, which is fine. Which is good in this particular case because it takes into account these two type of values. Okay. So while accuracy 0.7 and precision 0.67 are relatively high, this is not a good classifier. Why? Because the recall is high. The fact that the system is not able to catch an infected person twice, 2F negative, shows this is not a good classifier. One non-code infected person could transmit the virus to others without their knowledge. This is very bad system, okay? Because this system should have a false negative that is 0. We cannot tolerate this system. The F1 measure always takes a value between the recall and the precision. As I mentioned to you, this is due to the fact that the F1 measure is the harmonic average. That's the formula that we have defined it in the form of the recall and in the form of the precision. Okay, so we will tackle example 3 next on Friday next week, but I would like you to go over these set of slides and to look at them, to look at the importance of having a good classifier versus a bad classifier, when precision is more important than recall. And next time I will continue with an example, third example. If you would like, you can go over it. And then I will give an example for the confidence measure for confidence matrix for more than 2 classes for the system. So for the last value, so let me see here. I did not read a lot of your emails, so let me look at it very quickly. Do the numbers in the confusion matrix have to adapt? Yes, correct. So all the classes have to adapt to 100% of all the classes. Okay, every column sums to 100% for the positive or for the negative. So you have to sum up all the values. I mean, all the classes have to sum up for all the cases. For the rows, they have to sum up for the, in this particular case, the columns have to sum up for all actual positive cases. Every row should sum up for the actual cases. So that's the 100%, okay? And then what is here, 80 plus 5 is equal, what I did not understand this one here. Let me go to the next one. I think that one was supposed to be 10 in last cell of the row, in the rest sum to be 100, don't they? So I don't see which one here. I don't know which one he's talking about. I mean, yeah. So if you can email me and tell me which one you felt wrong, because I'm not really sure which one you are talking about, which matrix you are talking about. Look, which confusion matrix. So this confusion matrix here, so this particular number should be the actual number of real spams. This actual number should the number for all non-spams. So these have to be 100%, the summation of all those values. And for all these ones should be the total number of all the classes. Okay, so all the classes have to be included within that overall number for all the possible type of classes. Okay, page 13. So let me see page 13 very quickly. Okay. Yes, you are right. Yeah, you are right. Yeah. So that's correct. Yeah. I mean, these things have to sum up to 100%. Yes, that's exactly the case. Each column sums to 100%. You are completely right. Yeah, so let's see here. So 11 plus 12. Yeah, so these are wrong values. So yes, very good point. Yeah. So the whole values for the table should sum up to 100%. You are completely right. Yeah. Okay. So I will fix that table for that particular confusion matrix. And when I'm going to talk about the confusion matrix, so I have another example. I think it was labeled correctly, so this possibly was taken from a wrong table. But you are completely right. Each column should sum up to 100%. Okay, so thank you very much, and please feel free to email me if you have any comments on the slides. And I will continue on these slides on Friday, and I will give you some further insights on how to utilize them, when to utilize them, when the F measure is good, when the recall is good, when the precision is good. I have shown you today the recall versus the precision, and I will continue with that next Friday, and I will speak as well on the best possible type of regressor, type of errors, and I will fix this error, this table for you as well, to make sure that it is posted correctly. Thank you very much again for showing up today, and I'll see you on Friday next week. Thank you very much. Bye.